A vector is a line segment with an arrow tip on one end. It has an initial point or tail where it begins, usually called point of application, and a terminal point or head where it ends. The vector is defined by its magnitude, or the segment's length, its direction, that of the line containing it, and its pointing or sense of direction, indicated by the arrow tip. Many physical quantities are described using vectors. Here we see some examples. In a graphical way, we can add two vectors by placing the point of application of one of the vectors on the end of the other. The sum is found by joining the tail of this latter vector with the head of the displaced vector. If the two vectors are parallel and pointing the same way, the sum will also have the same direction and pointing, while if they have opposite pointing, the pointing of the sum will be that of the vector with the largest magnitude. When the vectors have different directions, the direction of the vector resulting from the sum is different from either of them. Another way to graphically add non-parallel vectors is this one. If two vectors are applied on the same point, we draw a line parallel to each one of them starting from the tip of the other vector, in such a way that both lines cross, forming a parallelogram along with the vectors themselves. The diagonal of this parallelogram, going from the point of application to the point where the two lines intersect, represents the sum of the two vectors. This method is known as the parallelogram law. Vector decomposition is the opposite to vector addition. The goal is to find the two vectors that can be added to produce another. This image displays the most common decomposition into vectors that are perpendicular or orthogonal to each other. It is very common to represent decomposed vectors in terms of unit vectors, which are perpendicular to each other. A unit vector is a vector along a given direction whose magnitude equals 1. It is used to indicate that direction in space. In this formalism, the component vectors from vector A in the image are written this way. The resultant or sum is then expressed like this. It is also very common to express vectors in terms of coordinates, so that the decomposed vector is indicated by the values of each of its components, separated by commas. We see that the vector is forming a right triangle with its orthogonal components. This allows us to find the component values using the trigonometric relations we already know. Or vice versa. If we know the components, we can find the magnitude of the vector and its direction, given by the angle. Vector decomposition makes it quite easy to add vectors analytically. Let's see it with an example. Graphically, as we have seen, it is enough to shift vector B to the head of vector A, and then draw the resultant vector. If we decompose the vectors, we will have two pairs of parallel vectors. Hence, we just have to add the vector components along each axis to find the corresponding component of the resultant vector.